So the question of scale is very important in seismology, and we're very often wondering whether observations over a small system, which may be a small earthquake, or it may even be a lab experiment when you may be looking at maybe a few centimeters or 1 meter of fault, we often ask if those results can be applied to much larger scales of hundreds of meters or kilometers or more, which are relevant to for larger earthquakes. And one of my research projects was very much looking at this question. And what we were asking is whether we expect the same behavior in a statistical sense, regardless of the dimension of a seismic source. In other words, if you have a small seismic source, imagine like a small fault patch which tends to break into earthquakes, is the statistics in that case comparable to the behavior you would expect on a much larger fault? And in general, what controls the behavior of this seismicity? Do we expect, for example, periodic seismic cycles in which earthquakes of a similar size repeat in a quasi-periodic fashion? Do we expect temporal clustering, in which case we may have periods with more earthquakes, periods with more quiescence? And how does the size of the source affect this behavior? And we actually find that it has a very first-order effect on the behavior. And we found that you can only get these very periodic sequences on faults or seismic sources which are quite small. As soon as a fault is sufficiently large, you start getting spatial variations in stress. So you may have some parts of the fault where the stresses are high, other parts of the fault where stresses are low. And because of that, you don't get a simple sequence in which each earthquake looks the same. Instead, you get a lot of smaller earthquakes, and you get fewer large ones. So you start getting very kind of interesting statistical patterns where you have this wide range in earthquake sizes, and you also see a very different behavior in time. So you don't have these periodic sequences anymore. You get much more random behavior, you get some temporal clustering, and so on. And this is actually very similar to what we see in nature. We almost never see this very periodic behavior. And so my work has been, the goal of this project was really to understand why and provide some fundamental physical understanding, where we start from a description of friction on the fault, some relatively simple laws that tell you, how the resistance of the fault, of how friction changes with time, and this allows you to start making sense of all these complex statistical patterns in nature.